Let's talk about error propagation. Error propagation is the process of translating individual errors that are taken in an experiment or in a calculation throughout your entire procedure. In chemistry, error propagation typically is encountered through using experimental equipment. Let's take a look at the following problem. Assume that you are given a pipette that dispenses 1.0 plus or minus 0.1 milliliters, and that we need 4 milliliters for an experiment. Part A starts by asking, what is the largest the total volume could be? So if the pipette is giving us 1 milliliter in each measurement, and it has an error of 0.1 milliliters, this means that the maximum volume in one measurement the pipette can dispense is going to be 1.1 milliliters. And we know that we need 4 milliliters for the experiment. So we have to use the pipette 4 times in order to get to this volume. And so if we take 1.1, which is the maximum volume in one measurement, and multiply that by 4 for our total number of measurements, that means the largest the total volume could be is 4.4 milliliters if we maximize the positive error that is given to us. Now, let's take a look at the second part. What is the smallest the total volume could be? Well, this is similar to the first part, but now we're just using the negative error. So the smallest possible volume that we can get in the first measurement is going to be 0.9 milliliters. And now if we carry that through after 4 measurements, the pipette's going to give us 3.6 milliliters if we're taking 0.9 every time. So the smallest the total volume could be is 3.6 milliliters. Now, with the first two out of the way, we have these two limits, per se, of our possible bounds in this measurement in our experiment. So given these two limits, write down the answer as x plus or minus y milliliters, and then provide x and y in this statement. So this part's pretty simple. All we need to do is write down the middle of these two limits, and then write this as plus or minus 0.4 milliliters. So we put 4.0, was a bad 0, 4.0, okay, and that's going to be our x, and then we're going to put our error after that, okay, because we know we're getting 4 milliliters because this is our total volume for the experiment, and then the total possible error, which matches up with these two bounds, is going to be 0.4 possible on either side. And so that's the answer for this part. Now, let's take a look at the last part of this question. Compare the relative error in your answer in the previous step to the relative error in the pipette itself. Did it go up? Did it stay the same? Or did it go down? So when we think about relative error, and I'll write it up here, our formula for relative error is simply the error over the final value. So when we think about the error or the relative error in the pipette, we know that the value we're trying to get in the pipette is 1 milliliter for our one measurement. So that means this 1 milliliter is our value, and the error is 0.1, which is after our plus or minus sign in the problem above. Okay, so for our relative error for the pipette, our error is 0.1, and this is divided by 1, which is our total value. Okay, and this is going to be equal to 0.10. And this is our answer for the relative error in the pipette. Okay, now our relative error in the previous answer, we see that we have 4 right here in the first part, and that's our total value. However, the plus or minus 0.4 is our total error in this step. So we can write out the same thing. 0.4 as our error over the 4 milliliters. Okay, and as you can see, if we work out the calculation here, we'll get 0.10 as well. So we find that our relative error in both cases, this is the previous step, they're actually equivalent. So those equal the same thing. So we can circle here that they stay the same. Okay, so before we move on to the next section of this problem, I want to make a quick note. When I mentioned the formula for relative error, I'll just write relative E, that was equal to the error over divided by our value. And this is similar to another formula that you may be familiar with, and this is the percent error formula. And you may have seen it written slightly differently, but one way to write it is the same way, error over your total value without the error. But now we take that times 100 in order to get a percent. So the relative error is actually hiding out here in our percent error formula. However, we're taking it times 100 now in order to turn it into a percent. A more accurate method for error propagation involves what's known as the root mean square, or RMS method. So this is what part B of our problem involves. It states that using the root mean square, or RMS method, write down a new answer for the same problem as x plus or minus y in milliliters, and give x and y. So let's start by looking at the formula for the RMS method for error propagation when we're adding together subsequent errors. It states that our final error after a series of measurements will be equal to the square root of the sum of each individual error squared. So we can apply this formula to our original problem, which is listed again here. So each EI, or individual error, is also known as an absolute error. And this is what we see listed at the top as 0.1 milliliters, and that's the error in the pipette itself. So we know that we have to use that pipette 4 times to take 4 measurements for the 4 milliliters that we need in our experiment. So let's first start by writing our 0.1 in the place of EI. And then since we know that we take 4 measurements, then we'll have an 0.1 absolute error 4 times. We'll multiply this by 4 as we're summing up these errors according to our sigma notation here. Okay, so if you work out this calculation here, you'll find that you'll get the square root of 0.04. And if you put that in a calculator, or if you do it in your head, that'll be equal to a final error of 0.2 milliliters for our 4 measurements using the pipette. Now you may have noticed that this final error is less than the final error in our last step in part A. And using the limits in that case, we got a final error of 0.4 milliliters. As you can see here, this final error using the RMS method is less than that. And we'll talk about the ramifications of that and why this occurs in part C. But for right now, let's go on to the last part of part B here. That states, compare the relative error in your answer in the previous step to the relative error in the pipette itself. Did it go up, stay the same, or go down? So this is the same question as you saw at the end of part A. Let's restate the formula for the relative error. It's equal to the error over the value. So starting with the pipette, this is the same exact formula as last time and the same exact calculation. For the pipette, we know that the error is 0.1 milliliters. So that goes right here, divided by the final value that we get with one measurement, which is 1. So this leads to a relative error of 0.10 for the pipette. I'll actually make that box a little bit smaller here because we're going to want to circle an answer. Okay. And then the relative error using the RMS method, again, equal to the error over the value. The error, you can see right here, we wrote it, our final error after 4 measurements is equal to 0.2, and that is divided by our 4 milliliters that we need for the entire experiment. That's our measured value. After working out that calculation, we'll be left with 0.05. and as your relative error, utilizing the Rms method for error propagation. So as you can see, between these two values, the relative error went down. Part C. Now generalize the RMS method for n measurements. State whether the relative error goes up, stays the same, or goes down. So let's start by writing down our answers for the uncertainty in our measurements for part A and B. So in part A, we found that we had 4.0 plus or minus our uncertainty of 0.4 milliliters. So this was for part A. And then in part B, we found that we had this 4.0 milliliters, which was our final value that we needed for the experiment, plus or minus an uncertainty of 0.2 milliliters. And this was actually the answer for the first section of part B. On the last slide, I realized I forgot to include it. So here it is right here. That's the part where it asks about the x plus or minus y milliliters. And so now let's head back. Let's think about part C here. We need to generalize the RMS method for n measurements. So if we look at part A, in part A, we're assuming that we're taking the maximum error for every measurement, which is going to be plus or minus 0.1 milliliters. But in reality, as we see in part B, this error is significantly less, or actually half of the error or uncertainty from part A. So what we can conclude from this is that the errors don't take on the maximum potential error during each measurement. Instead, errors are random, and this means that the errors often offset each other, so that you can have one that's maybe half of a 0.1, but you can have another that's even smaller than this. And so that since these errors are random, you'll never get this maximum error, or it's very unlikely that you'll get a maximum error like we saw in part A. And the random errors will tend to offset each other, and you'll get one that's closer to this root mean square approximation that we saw in part B. So for n measurements, okay, for any number of potential measurements, as you increase the number of measurements, your random error is going to increase, and that means you'll get more errors that offset each other. For each plus error, you'll have more minus errors, and those will offset each other. And so that means as n increase, your relative error, okay, or your E relative, is going to go down, okay? And then, so we can circle goes down here. And this is again because as we increase the number of measurements, more measurements will offset each other, and the relative error will go down. And this is really, this relationship is what comes out of the root mean square approximation in part B. And this is what we see in reality, unlike in part A, which is an unrealistic scenario. So the root mean square approximation is an accurate representation of error propagation in the real world. Okay, this concludes our discussion of error propagation, the root mean square method, absolute error, relative error, and percentage error. I hope you found this video to be helpful. If you have any questions, be sure to leave them down below. Thank you again for watching, and I hope you have a great day.